Welcome to NPTEL. Myself Dr. Joyanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. This week we were discussing about nanomaterials and nanocomposites. We have realized that specifically this nanomaterial means that they are in the length scale of 1 to 100 nanometer. However, there are several unique properties that can arise because of the size effect, means the smaller in the size of the particle. Irrespective of its application, whether it is a structural purpose or biomedical purpose, it does not matter, but these property changes or modulation of the properties is not only due to the small size, but small size effect on many elementary consequences. And today we will be discussing on those elementary consequences, the reason behind modulation of wide range of properties. So, let us start the discussion today. Now, if you look at a microstructure of a bulk nanostructured material, you see here these are, let us say, 5 or 10 atomic layers arranged in a crystalline form, and these are the neighboring nanocrystalline grains. But interesting point here that the black grains are in the lattice and the surface atoms are represented with the empty one, the white one. And one can easily see that if the size scale is smaller, there is how many spacing 1, 2, 3, 4, 5, 6, 7. So, maximum 20 nanometer within that scale or 10 to 20 nanometer. So, the amount of this grain boundary is very high. So, by looking at such a microstructure, one can easily speculate that around 50% grain boundary and 50% grains are present or area covered by the grain boundaries. So, this is a very simple metallurgical aspect of a grain and grain boundary area. However, the large portion of the material that is associated with the surface or large number of surface atom, this is one of the very important aspect in case of nanomaterial. So, to be in short and brief, one can look at these elementary consequences which modulate the properties of nanomaterial. So, very important are the surface, because we can see here whether these are individual particle and these are the surface, one can estimate the number of the surface atom, that could be very high. Now, there are other phenomena associated with this, like thermal phenomena, diffusion, which is also one very important elementary property. Now, each and every particle has their own vibration, and vibration depends on the length scale of the object. Now, the typical size effect are surface to volume ratio, the structural magic number, the surface curvature, because the curvature become much and much, radius of curvature become much and much smaller in case of nano than a micro, right. So, this R is quite small in case of a nano, as well as there is strain confinement and the density of states, or let us say the quantum effect. So, these are very important aspect of any of these material when we modulate the structure and bring it down in the nanometer scale. So, in case of surface related property changes, we can simply start with very fundamental calculation. It is for sure that once the particle size is small, the surface area around a particle, whether it is sphere, whether it is a cylinder or it could be a cube. So, the surface area will be higher, but we can simply estimate it, and the relative surface by volume ratio for a sphere, let us say the area by volume and 4 pi r square by 4 pi r cube by 3, which comes around 3 by r. Here r is basically the radius. Now, in case of a cylinder, if the length is h and I have r is the radius, then we can reach 2 by r. Now, in case of a cube, if the length of is L, one of the edge is L, then we can get actually 6 by L. And now, one can take this equation and plot it here A by V in the y axis, and in the x axis this is the dimension, let us say in case of R or L and so on. So, here you see that up to 40 nanometer these values are okay or relatively lower, but it suddenly jumps irrespective of sphere, cylinder and cube, it suddenly jumps above 1. This is a very high value. It is for sure that cube always has a higher surface area than a sphere. Okay. There is no doubt, sphere always has the lowest surface area for the same amount of volume if we convert this volume or transform this volume into a cube. So, once we reach below 20 nanometer scale, the surface area is very high. But one can think about how this surface area really affect. Yes, we have shown that surface area increases a lot or relative surface by volume ratio increases a lot, but is there any other elementary consequences related with the surface? Yes, the answer is yes. Now, let us think about a surface area of, let us say or in terms of molecular weight or number of some particles. How really does it affect? We can see here the net surface area with the number of the particle per mole, and here A is the surface area of an individual particle, let us say. And then we can reach to this such a equation 6 m by rho into d, which basically said where m is the molecular weight, rho is the density and d is the particle size here. So, d is the particle size. Okay. So, now I am estimating this in terms of the molecular weight, means 1 mole of particle how much total surface area is available. We can estimate this in terms of giving you an example that will be good. So, let us say a spherical particle with a 10 micrometer diameter, okay, and this 10 micrometer diameter which has to be reduced to a group of particle of 10 nanometer, okay, assuming that the volume of the particle remain constant. Okay. In that a case, we have to create new surface, yes, because a 10 micrometer size particle has to be divided into multiple pieces. However, if you just take the ratio of the same amount of volume, so a particular 10 micrometer particle has to be divided how many number of pieces, so that we can generate 10 nanometer size particle. So, here n is the volume which remains same of a 10 micrometer and 10 nanometer size, and we can reach to 10 to the power 9 number of particle, means I have a particle which has a let us say 10 micrometer size, and if I make it 10 nanometer, then I will get 10 to the power 9 number of such particles. Now, let us come back to the surface area. In case of surface area A, which will be 3.14 into 10 to the power 8 nanometer square. In case of the area of a 10 nanometer size particle, which is basically 314 nanometer square. Okay. And now, the interesting thing that these 10 to the power 9 number of such particle existing. So, we can estimate the total amount of the area covered by, or the surface area available for 10 nanometer size particle, which is 3.14 10 to the power 11. So, you can see here this is almost 3 times or 10 to the power 3 times higher, means we can increase the surface area by 1000 times. This is really huge. So, just a difference between a 10 micrometer size particle and 10 nanometer size particle, we increases the surface area by 10 to the power 3 times. Now, whether any other aspect is associated with it, means I have created a high surface area, but if we think about that on a nanoparticle, and how much volume is associated near to the surface of a nanoparticle, and how much is that, we can estimate it. So, the R star we are creating, which is basically the ratio of the amount of this volume divided by the net volume. Let us say d here is the particle size. Okay. So, and the thickness here is the delta. So, delta is the thickness. So, I have to reduce, so 2 delta, okay. And so the dq minus d minus 2 delta, which is basically this amount of this particle, the diameter of this particle divided by dq. So, it will come 1 minus d minus 2 delta by d into q. Okay. So, if we simply give an estimate of, in case of some length scale, let us assume that I have a spherical particle and I am considering a thickness of delta, that is 0.5 nanometer, and let us say or 1 nanometer. Two cases I am considering, whereas the particle size is 5 nanometer. So, d is the 5 nanometer. In that case, you will find that the volume ratio of the surface and the bulk volume is almost 48% in case of 0.5 nanometer thickness, and it is almost around 79% in case of 1 nanometer thickness. And such a high volume is available on the surface of a nanometer, of a nanoparticle. So, this is quite high. Now, here I can take the simple equation and plot it. Here again I have basically the R star and with the particle diameter. So, let us say from here for the same 0.5 nanometer it will come somewhat 48%, and in case of a 1 nanometer surface layer, then R star will come to 79%. Here please remember R star is the ratio of the volume available at the surface divided by the bulk volume. Now, again we have calculated, but now what is the elementary consequence? Yes, this simply said that the majority of the atoms, they are present at the surface. So, means 80% volume if it is occupied at the surface, then majority of the atoms, because the volume consisting of the atoms. And we all know that the surface is related with a energy, we call it as surface energy. So, high amount of energy associated with that surface. So, these are the two very important part that we have derived from this discussion. Now, let us have a look at what really happen in case when there is a high amount of surface energy or atoms on the surface. Let us first assume that I have a larger particles and I want to create a nanoparticle, or vice versa, I have nanoparticle. How is its surface energy that we can back calculate by thinking in such a way that I have a bigger size particle, I have broken that particle into very teeny pieces. For each and every times I break a larger particle, I have to create a surface, and if I have to break and create a surface, I have to break the bonds, atomic bonds. So, each and every atomic bond is related with some energy, and that is here is one of the very elementary consequence. So, let us have a look at this diagram. Here what I show you that initially they are the same particle and I want to create a surface. So, I have to break this bond between these two atoms. So, if U is the bond energy, then for each particle I have to consider U by 2. So, here is U by 2 and here is U by 2 for each particle, right. So, the net surface that I have just shown you few minutes ago, that if that is the net amount of for a particular molecular weight, if the total surface area I have, that is 6 m by rho into d, and now I have to multiply it with a specific surface energy. Okay. So, then I can calculate the total surface energy of one molecular weight number of particles, right. So, once again the small particle, if I repeat the same thing that I just told you, the small particles are produced by breaking the atomic bonds of a large solid into smaller parts. Now, between each and two particle or the atomic bonds in the lattice, the energy of the bonding, let us assume it is U, which is shown here. And so, for each broken bond of the new surface, the energy is U by 2 for each particle, and the number of such broken bond per unit area, if it is n star. Let us say I have how many number of broken bond, here it is n star, number of bonds. So, then I can multiply that n star multiplied by U by 2, okay, for a single particle. And then what will happen? So, the contribution of the surface energy here, that there are one part will come from the broken bonds. So, this is actually one of the contribution, that is gamma 0 on surface energy will come from the broken bonds. Now, there are some other component that comes to that surface energy. Yes, due to the reduced number of neighbors, each surface atom will give you a force on individual particle. So, it is like you are stretching a rubber and a force is acting on the surface, and please try to think this is not at all a hydrostatic stress I am talking about. Okay. It is only related with the surface. So, once if A is the area that is occupied by an atom on the surface. So, I have a surface and I have atoms here on the surface, and then there is a force, and this force for a particular atom, let us say the area is A. So, the net stress will be F by A. So, the contribution of the surface stretching, okay, this is the stretching of the surface that gives you a relative strain, that is epsilon s, and related with the surface energy. So, the net surface energy has two major contribution, one come from the broken bonds and another one comes from the stretching or the surface stress. Okay. So, these two components are very, very much important. Now, once again I have a very small particle size and I have a high surface energy. Is there any elementary consequences related with if two particles join together or not, or whether joining of two small nanoparticle is energetically favorable or not, that become the question. So, the again we have to calculate the surface or the energy of the particle, and then if I join together two particle, how much. So, initially I have started with a bigger particle, I have broken into multiple pieces and I made a nanoparticle. Now, I am thinking joining two nanoparticle, whether that is energetically favorable or not. So, in that particular case, please try to calculate and think about the surface energy. So, the surface energy per particle, let us say there is a delta U surface energy when we are joining two particles, let us say, means I have one case where the two particles are separate, and in other case I have two particles, they are basically coagulated. So, I have one area here and energy associated with it, and when they are in individual form. So, this is a coagulated forms that we are talking about. So, now here after coagulation the size of the particle will be decoagulated, which I shown here, and the individual particle has a size of d. So, the surface area into the change surface area change multiplied by the energy, that will give you the estimate of the net change of the surface energy, that is delta U. So, here you see that it will somehow end up with pi gamma and d square into 2 minus 2 to the power 2/3. So, 2 to the power 2/3 is linked with the decoagulated and the d. That is basically a simple equation mathematical that you can do some homework. However, if such a case occurred, then the surface will release the energy. So, where that energy will go? Yes, if there is a release of the energy and if it is a adiabatic in nature, then it will increase the temperature of the particle, isn't it? So, in that case the energy that is released due to joining of two nanoparticle, joining means I am talking about coagulation. In such a case, then the density and the Cp, if we simply think about, then it will give some value of gamma into rho Cp 2 minus 2/3 by d. Okay. The same phenomena we can think about in case of sintering operation, means I have two particles, they are joining together and this is a simple sintering phenomena. Okay. Now, let us have a look at how much this value of temperature rise is associated with when there is a coagulation occur. You can have a look here that the particle diameter of 10 nanometer, when it reaches to 1 nanometer size, the temperature flash which occur adiabatically can reach up to 300 Kelvin. This is a high rise in the temperature just because of joining or coagulating two particles. Okay. Here I also show you a image where coagulation occurred in case of 2 gold nanoparticle. So, in that case you can see that this is a gold particle and this is another gold particle. So, after some time during coagulation process they come very much closer. However, you can see that the orientation has changed. Yes. So, here the atomic planes was aligned with the incident electron beam, and here this is a differently oriented. Now, I basically have a such a case almost like joining, and it is almost now become a spherical shaped particle. However, there is no new grain boundary has formed inside the particle, okay, or outside, but these two particle basically changes its orientation during joining, or let us say during coagulation. Now, let us consider about the energy released during sintering. So, the same energy, that is multiplied by m into 6 into mu by rho into d final. D final means after coagulation, okay, after sintering. So, here will be one multiplication factor, that is d final by d minus 1. So, this d final by d, okay, this must be greater than 1, and here I will have some value. So, as long as the d final by d is greater than 1, the surface energy released during the grain growth is proportional to the inverse of the particle size. So, this is one very good observation or elementary consequences when two nanoparticle or also other particle in case of sintering they join together. So, this is another important aspect. However, there are also other aspect. I told you that if I have a very high volume located at the surface, then the number of atom present at the surface is very high. Now, please have a look at the left hand side image. Here this is a typical face centered cubic unit cell. So, I have atoms at all the corners, these are the corner atoms here, here and here and here, and now I have basically some face centering translation here. So, the atoms are positioned at the center of each faces, each of the 6 faces. So, each of the 6 faces there are 6 and the corner atoms are 8 in case of FCC unit cell. Now, let us assume that this is itself is a nanoparticle, means I have a particle which is in the scale of let us say 0.5 nanometer or something like that. And then mathematically we can calculate how many number of these atoms present at the surface or how many number of atoms present in the bulk, and this number are basically the structural magic numbers. I will show you within a minute if you have a look at these two equations about these magic numbers. So, the surface total is basically 12 n square plus 2, whereas the bulk atoms are 4 n cube minus 6 n square plus 3 n minus 1. These are simple mathematical equation you can also derive. And then the unique thing here that if I consider a single unit cell to be a single nanoparticle, then I have 1 here. So, I will have basically 14 and the bulk atom will be 0, is very clear. And so, this means I am talking about n is equal to 1, okay. Small n is equal to 1 means 1 unit cell representing 1 particle. So, here I have 14 surface atom and the bulk atom. Just have a look at the ratio of surface atom, okay. It is 100%, all the atoms are present at the surface of that nanoparticle. Now, if I join 2 and then I increase the number as 2, then it will decrease by something like 80%. So, I have 50 number of surface atom and 13 are present in the bulk, and you can see here that when n is equal to 4 means I have a very good number of or size of a particle, means let us say something in the scale of let us 0.4 nanometer multiplied by 4. So, this is let us say length scale I am talking about. So, something like 1.6 or let us say 2 nanometer size. In that scale I basically have 194 number of surface atom and 171. So, it is now almost like surface to bulk ratio is 1.13. So, the same number of surface atom and the same number of atom present in the bulk. So, here we only consider the atoms of one atom on the surface. So, these are the number, and if we increase the number up to 100 actually, even there are around 2.913% of the surface atoms are present, and these are the structural magic numbers. So, a large number of atoms present on the surface. Now, if we consider that in case of a FCC it become a other type of structure, same FCC, but we basically the smallest FCC nanoparticle that can exist inside a cubo-octahedron, because we have considered here a cube actually, and here these are the cubo-octahedron particle. So, here also the structural magic number we can express. So, here the minimum of this n is equal to 2, because 2 cells are there, and then the bulk atom is 1, and if we increase it, then you will see that the ratio almost becomes similar, means the surface to bulk ratio, when we consider that 5 is the value of the n, and I have 162 atoms to 147. Here almost 52% surface atoms are present, and which again reach up to 3%. So, a very finite and large scale almost 3% is there, but if we reduce the size and go to a smaller scale, then majority of the atoms are present on the surface only. And these are the very basic elementary consequences of a nanoparticle. So, with this we finish our discussion today, and we will continue our discussion in the next class. Thank you.